Hello, this is the Med Dude, and today we're doing Physics Unit 1, January 2009. So let's get right into it. So question number 1, we have the table shows some physical quantities. Which row correctly identifies scalar and vector quantities? So they've given us some quantities, so the first thing we can do here is that just check whether they're scalar or not. So is distance scalar? Yes, it has a size and no direction. Time has a size and no direction. Velocity has a direction, so it's automatically out of our options, and C is already out. D, we also know, has no direction. All right, so vector acceleration, yeah, acceleration is a vector, so just by that I know that A is probably the answer, but we'll just check anyway. Speed is not a vector because if it was, it would have a direction, and that is velocity, not speed. And similarly, force is a vector, but we already ruled out C, so C is already out, and power is not a vector. So the answer is A. Question number 2. A cyclist traveling at a speed of 4.2 meters per second, 4.2 meters per second, that's important, accelerates as 1.1 in a time of 7.4. The distance traveled is. So they're asking for what? They're asking for what the distance traveled is. So this is a classic case of SUVAT equations. So you have SUVAT equations. So we have S is our distance that we're trying to find. U is given to us 4.2 meters per second. V we don't have, so we just put an X. A we know is 1.1, and even time we know is 7.4. So we want an equation that has S, U, A, and T. And that equation is S equals UT plus half AT squared. Now all we have to do is just substitute our U and T and A. So that would be 4.2 times 7.4 plus a half times 1.1 times 7.4 squared. And that should give you 61.198, which we can say round off to 61 meters to 2 sig fig. So by that calculation, we know the answer must be C. All right. So the next question. So which of these units is the same as Newton? Now, when we talk about Newton, the quantity for Newton, we're talking about force, aren't we? So forces are usually measured in Newton. Now, just an easy formula for force is what? M times A, mass times acceleration. Now, what are those units that we have? We have kilogram times meters per second squared. Now, because of that, I know that the answer must have kg and ms minus 2 meters per second squared. So when I look back at our options, I should see an answer that has the same exact thing. So the answer should be kg. It should be kg meters per second minus 2. So which one is that? So is it A? Nope. It's B, kg ms minus 2, ms to the power minus 2, and not meter squared, not meter squared. So A is not the answer, B is the answer. All right. So question number 4. A student is asked to determine the output of a motor as it lifts an object. He measures the height through which the object is raised, the time taken, and the weight of the object. So the question asks us to find the power. He must calculate what? So in order for us to calculate power, we need to know what the formula for power is. Usually the formula for power is power equals work done over time, right? Work done over time. So automatically I know that the denominator must be time, and just using that logic, right, that the denominator must be time, I can deduce that A is not the answer because it does not have time in its denominator. B is probably the answer because it has time on the denominator. What about C? Nope, has height on the denominator. And not D because it has time and height. We have time on its own in the denominator. So just by using that logic, we can conclude that B is probably the answer. And it is in fact the answer. Now, why is that? Now, the work done is equivalent to the the energy you use for the task to be done. Now the energy we use is related to the gravitational potential energy, which is we usually say is mg times h. Now mg is the same thing as weight, which they tell us in the question. So they tell us that they have an object, right? The motor lifts the object. So the things that we're given are weight times height divided by time. So that's how we calculate the power, and that's why B is correct. Question number 5. A football is kicked at a speed of 12 meters per second at an angle of 35 degrees to the horizontal. So now let's draw that first of all. So here we have our 35 degrees to the horizontal, and this is our 12 meters per second velocity of the football. All right. So they're asking us to find the horizontal component. Now the horizontal component, we usually say, so this is the horizontal one, horizontal, or the x plane, or the vertical, or the y plane. Okay, so just the key thing to note here is that whenever we want the horizontal component of a velocity like this, a projection, we always do this. So it's always the velocity times cos theta, and whenever we want the vertical or the sine vertical, we refer to the sine of the angle, so that becomes v sine theta. So in this case the horizontal component, so we can write horizontal component of Vx should be 12 cosine 35. So we just go back to our questions, and we can see that A is the only one that refers to 12 cos 35. So this is referring to the vertical, which we don't want, right? This is to confuse you, and this is also to confuse you. All right. Question number 6. The diagram shows a graph plotted using the results from an experiment, which is the metal wire was stretched. The gradient of the graph, so that's important. So the gradient, right? Delta y over delta x, right, is equivalent to Young modulus. So I'm just going to write Young modulus. So what are they trying to find? They're asking for the correct labels of the axis. Now we know from knowledge that Young modulus is actually stress over strain, right? Now because we know that, and because we know that delta y or delta x is equivalent to the gradient, we can conclude that that stress corresponds to y, right? So we can say that stress is the same thing as y, and strain is the same thing as x. So now we just need to find the choice that has stress as y and strain as x. So A does not have stress or strain, B does not have stress or strain. Let's look at C. C has stress or strain, but what is y? Y should be stress? Nope. So D is the only one that has y equals stress and x as strain. So our answer is D. All right, question number 7. A pigeon of mass 0.45 kilograms is flying with kinetic energy 58 joules. So the key thing to note here is mass and kinetic energy. What they want from us is the speed. Now the only thing I can think of is writing down kinetic energy, which is half mv squared. Now what do we have? We have the energy in joules. We can just substitute, and we have the mass, which is 0.45. So all we can do now, we can find what the velocity is, right? We can find the velocity. Now we can rearrange to find the velocity. So what we can do is, we can times both sides by 2 and divide by 0.45. So we will get v squared equals, so we times both sides by 2, right? Times by 2. So this becomes 2 times 58. And then we divide both sides by 0.45. 0.45. So this is where I get the divided by 0.45 from. And then we do v equals, then we just square root 2 times 58 all over 0.45. Now just to note that you don't get marks for showing you're working out for the multiple choice questions, so it doesn't really matter if you have the correct answer or not. So like, by correct answer I mean in the paper, because all what they're looking for is you have the correct option ticked. So don't forget to do that. So square root of 2 times 58 all over 0.45. That gives us 16.055, which we can round to 16 meters per second. So our answer is C, because A is 8, B is 11, and C is 16, so C is the answer. Okay, a ball bearing is dropped through a liquid, and its terminal velocity is measured. The experiment is repeated at different temperatures. Which row correctly describes the second experiment? So we have a bunch of rows, and what they're trying to ask us is which one is correct. Now this looks like they're trying to ask us what's the relationship between temperature and viscosity and terminal velocity. So let's just write that down. So they're asking for temperature, viscosity, and I'm just going to write V term, right? Terminal velocity, the V term. We know that temperature is directly proportional to viscosity and inversely proportional to V term. So what does that mean? That means that if our temperature goes up, our viscosity goes up, but our V term goes down. So by that logic, we can answer the following questions, right? So we have a scenario here. So if temperature decreases, so I'll do it in a different color. So if temperature decreases, we know that viscosity should also decrease, and we know that terminal velocity should increase. So let's see if when we lower the temperature, so if we lower the temperature, what happens to viscosity? It should decrease. That is not the case. So we can already get A out of the equation. Same thing with B, so lower. Viscosity is greater. Nope, that's not what we want, so we can get rid of it. So now we're looking at the pink one, right? Now we're looking at the pink arrows. So if we increase temperature, yeah, we increase temperature. Viscosity increases, yep. Terminal velocity decreases, yes. So we know that C is the correct answer. The third one is obviously wrong. The last one is obviously wrong, because if we increase the temperature, we should also increase the viscosity, but it says smaller, so that's wrong already. So C is the answer. Question number 9. Velocity can be found from the following. So it says area under the displacement time graph. So that's not the answer, because this is actually the distance, or the displacement. This is distance. Area under a force time graph. Nope, this is referring to impulse, which is not what the question is asking. The gradient of a displacement time graph. Now that sounds like that would be the answer. Now why is that? That's because if we have a displacement time graph, right? So if we have a displacement time graph and we have the gradient, say, right? So this is S and this is our time. The gradient would be the change in S, so change in S over the change in time, which by definition is velocity, isn't it? It's the change in displacement over time. So C is correct. The gradient of displacement time graph. Now, the last one we can also ignore, because they're trying to confuse you at gradient of an acceleration time graph. If you've ever seen an acceleration time graph, usually they don't have a gradient, and when they do, it's not related to velocity, because acceleration is in fact the rate of change of velocity over time. So it's impossible for us to relate normal velocity to the gradient. Okay. Question number 10. A freely falling object on Earth has a speed of 5 meters per second. After falling a further 20 meters, its speed is what? So scenario time, we have an object, right? It's falling initially at u, 5 meters per second. After 20 meters, so this is 20 meters now. So 20 meters, we want to know what the velocity v is, right? So what's acting on this object? What things are acting on this object? So this is a classic case of another SUVAT equation. So we can write SUVAT, S-U-V-A-T. So the S we know is 20 meters, right? U we know is 5 meters per second. V we're trying to find out. A, we'll get to it. Time we don't have. Now, because the question says, it completely says, freely falling. That's a clue in itself, and it says on Earth. So we're referring to another force acting on the object, which is its own weight, right? So this is its own weight. Now, because its weight is acting on the object, there is an acceleration acting on the object, which is g, the acceleration due to gravity. Acceleration due to gravity. Now, usually this value is 9.81 meters per second squared, and it's usually negative or positive depending on the direction of the object. Now, because this is going towards Earth, right? So this is going towards Earth, right? This is going towards Earth. G must be positive because we're going acceleration due to gravity. We're going towards Earth, not away from it. So imagine if I threw a ball up in the air, the G acting on it would be negative 9.81 because you're going away from the Earth, and this acceleration is pulling you towards Earth, right? So we know that our A is positive 9.81 meters per second squared. So which equation can we use that links all of them together? That's going to be V squared equals U squared plus 2AS. So that would be U squared, so 5 squared plus 2 times 9.81 times S, which is 20. And that's V squared, so V would be square root of that. You can just do that, square root of this over here, and place there as well, so it's still there. So then we need to find use our calculators and find the velocity there is. Square root 5 squared plus 2 times 9.81 times 20. That gives us 20.43, a long decimal, meters per second, which we can round off to 20 meters per second. So our answer is B. All right, now we're done with multiple choice. Let's go to the theory section. So what's the question? Question number 11. The Saturn V rocket used in NASA's space program has a mass of 3.04 times 10 to the power 6 kg. It took off vertically with a thrust force of 3.4 times 10 to the power 7. Show that the resultant force is about 4 times 10 to the power 6. Now that's important. We need to find what? The resultant force. So I have this diagram here of the rocket, so it's more visual. Now if we have a rocket and it took off vertically with this force, let's just call it our upthrust, right? That's a term we're familiar with, upthrust. So if the upthrust is 3.4 times 10 to the power 7 newtons, there must be another force counteracting that, right? There must be another force acting on the rocket, which is in fact its own weight, which we can find out. So the resultant force should be the upthrust, right? Upthrust take away its own weight. Now why is it upthrust minus weight and not weight minus U? So why is it not W minus U? Now that's because the Saturn rocket is taking off. So imagine if the weight was more. So imagine if the weight was larger than U, right? It is bigger than the upthrust. Then the rocket would never take off, right? The rocket would never take off. So that means that the upthrust must be greater than the weight. So that's why we do upthrust take away the weight. So now we need to find the weight, right? So we find the weight. So weight is mg. So that's going to be 3.04 times 10 to the power 6 times 9.81. So our r would be 3.4 times 10 to the power 7. Take away the weight, so 3.04 times 10 to the power 6 times 9.81. Now the answer you'll get, we need to round it off to what? So the answer you'll get is, let's see. The answer we'll get is around 4.18 times 10 to the power of 6. Now, it's not actually 4.18, is it? It's a lot of decimals, but we have to round off to at least the most significant figure that we have in the calculation, which is 3 sig fig. And why is it 3 sig fig? Because you can see here 3.04 is 3 significant figures, right? It's 3 significant figure here. So this is the answer, 4.18. But is it the final answer? No. Because whenever we have a show that question, right? Whenever we have a show that question and they give us a value, we always need to round off to one more significant figure. One more significant figure. I could just write SF, sorry, significant figure. Then what they tell you to round. Then what the value is. So one more significant than what the value is. So if this was 4 times 10 to the power of 6, we need to round it to 4.2 times 10 to the power of 6 newtons. And why is that? It's because if you were to round 4.2 up or down to one significant figure, we would get 4. Now I think that's the basis of how that works, and that's why significant figures are a big deal in AS physics, and you could potentially lose a lot of marks. Just keep that in mind. All right, so calculate the initial acceleration. Now the only formula I can remember that relates the force and acceleration is F equals ma, right? Now which force are we going to use? We're going to use what we just calculated, right? So 4.2 times 10 to the power 6, right, equals mass, which is 3.04 times 10 to the power 6a. So a would be, you can see that both 10 to the power 6 is cancel, right? So you're left with 4.2 divided by 3.04. And the answer should be, so 4.2 divided by 3.04, that is 1.382 meters per second squared. And we usually round acceleration to 3 significant figures, so 1.38 meters per second is your answer. So that is your answer. So part C, after 150 seconds, the rocket has reached a speed of 2390. Calculate its average acceleration. Now, they're trying to throw you off because the average acceleration is just what the formula that we know, which is a equals v minus u over t. Now, what's the final speed we have? We know this final speed is 2390. What's the initial speed of the rocket? It's 0, isn't it? Because when it took off, it was 0. It didn't have any speed. It wasn't already traveling, was it? And the time taken was 150 seconds. So we can find this out. So 2390 divided by 150. So that is 15.93 meters per second squared. Now notice how I always write one more significant figure that I'm going to write in the final answer. That's because I need to know where I'm going to round to. So if this was, let's say, 15.96 or something, I would round to 16.0 meters per second squared. But that's not it, is it? That's not what I'm going to do. So for that reason, I always write in my answer sheet 15.93 instead of just the final answer, which is 15.9, because you can't have calculation errors. 15.9 meters per second squared. So that is that. Okay, so suggest why the initial acceleration and the average acceleration is different. Now, there are a couple of reasons why this could be. It's because as the rocket is, so this is the Earth, right? So if you imagine this is the Earth, as the rocket is leaving its atmosphere, right? Is leaving its atmosphere, what's happening to its weight or the pull towards the Earth? The weight is decreasing. Weight is decreasing. And because the weight is decreasing, right? Because the weight is decreasing, you can say that the pull towards the ground is also decreasing. Along with this, you can also say the air resistance is decreasing with altitude. So what you can say a couple of things. You can say the weight is decreasing. The weight is decreasing as you enter the atmosphere. As the rocket enters the atmosphere. And notice only one mark, so you don't need to write much. Enter the atmosphere. I'm just giving you multiple answers that you can write. So that is one. You can say, you can also say, so this is bonus, you don't have to write it, but you can also say that the air resistance is increasing. Air resistance is increasing. Is decreasing, sorry. Air resistance is decreasing. Decreasing with altitude. With altitude. Alright. So that's that. Now we move on to question number 12. The graph shows how stress varies with strain for a given material. Explain what is meant by the following terms. So we have the limit of proportionality L, we have tensile strength, and we have the yield point Y. Now, the simple definition for the limit of proportionality is when the graph, so this is when the graph stops obeying Hooke's law. When the graph stops obeying Hooke's law. That's one definition for it. You can also say that the force is proportional to the extension until this point. So you can say force is proportional to the extension, so delta x, until this point. Until this point. You can also say that. Now, what point is it on the graph? Now, let me show you on the graph. Now, that point is when it stops being linear. So, if I were to draw a line, right? If I was to draw a line, so you can see it's pretty linear. It's pretty linear up to here. It's pretty linear up to here, and it stops there. So, that point here. So, until here, we know that this is linear. So, this point over here must be L. This must be our point L. Let me just make it, this must be our point L. Because this is linear, the graph is linear until this point. Alright, so tensile strength. Now this tensile strength is very self-explanatory. So tensile refers to tension. So I'll just have like a small thing here. So this refers to tension. And this refers to how much load it can hold. How much load a material can hold. Now when you put that together, can hold, you get the following definition. You get the maximum load a material can support, right, before it fractures. So the main thing here is, so we just copy what we just talked about. So the maximum load a material can support before fracturing or deforming. Now the key thing here is before fracturing. That's the key thing, or deforming, because the first part of the definition is pretty self-explanatory, right? This part, the maximum load a material can support, we just found out from the word strength. Now tensile strength is the maximum load a material can support before it fractures. So the key part here is, I'm going to underline, so key is before fracturing and deforming. Now that's the key point here, right? So this was the other definitions that we had earlier. Okay, so the yield point. Now, the yield point, to put it simply, this is where the plastic deformation begins. Now, what does that mean visually? Begins at this point. Now, what does that mean visually at this point? Now, if I go back to the graph, you can see, I can explain to you, if I go much closer. Now, that point is referring to when the graph becomes more and more horizontal. So more and more horizontal. Now, what point is that? Let me show you. Now, that point that we refer to is, let me put it in red. Let me go back. So that point, if I can just zoom in Okay, so that point is this point. So you can see my red dot here. You can see where the graph becomes more and more horizontal is around it's around this area. It's around this area over here. Becomes more and more horizontal. Now where it becomes, it's a very fine margin. So you can say something along the lines of this. So you can say this is the yield point. This is where the graph becomes more and more horizontal. So for a small increase, so this is how I always used to remember it. For a small increase, so for a small increase in y, there's a big increase. There's a big increase in delta x. So you can always remember it as delta x is really big compared to delta y in this scenario. Now, the key thing to note here is that the answer is not the highest point of the graph, because the highest point of the graph is actually its ultimate tensile strength. So it is not the maximum point. So it is not this point. You know, some people might think it's this point. It's not, because that point is referring to the ultimate tensile strength of the material. No, this yield point is when the graph becomes super horizontal, and that is the case. From here to here, it's very horizontal, right? So if I go here, I can show you. I can say that from here to here, the graph is super horizontal, or it's a lot more horizontal than the other parts, right? So that's what you need to know when the graph becomes more and more horizontal. All right, so that is the answer. Now, part B we have just done is we have to mark down the limit of proportionality and the yield point, which I have just explained. So that's that. Now we can move on to question number 13. Question number 13. When a ball moves through the airflow is laminar around the front of the ball and turbulent behind it. State what is meant by laminar flow. Now, the textbook definition, or the definition that Edexcel wants, is pretty simple actually. The laminar flow, if you think about it, so if I have a disk here, right? And if I have laminar flow around it, it's going to be very, very, very streamlined, and it will have no change in direction. And that's what Edexcel wants you to say. They want you to say there is no sudden slash, you can write abrupt if you want, changes in speed or direction. Now, I can copy this word for word. I can copy this word for word for turbulent and just change one thing, and I'm going to get turbulent. Now, what is that one thing? That is this no over here. If I get rid of the no, it does make sense now, doesn't it? So if I have turbulent flow and that there is sudden change and abrupt changes in speed or direction, that means that it's the complete opposite of turbulent flow, isn't it? Turbulent flow goes everywhere, and that's the definition. So just by rule of thumb, laminar and turbulent are opposites. So if you know one, you definitely know the other. So that's where I'm coming from. So part B, the diagram shows a ball for which airflow becomes turbulent beyond points A and B. Add to the diagram to show the airflow around the ball. The ball is moving to the left. Now I got this diagram over here. Because I thought this is more visual than the ball given to us. So these things are irrelevant to us. So you can see in the exam, you can just put, they want at least 3 lines, right? So they want at least 3 lines that are they're pretty straight. And after this point, it goes crazy. That's our 1, that's 2, that's 3. So what the marksman wants is at least 3 lines, right, that correspond to the type of direction or type of flow that you can see. I just got this diagram here just to illustrate what a ball might look like, because if you see this diagram, you can't really visualize a ball to being moved to the left. So this is a better indicator of how you should visualize it. So part C, it is suggested that dimples on a golf ball decrease the area which there is turbulent flow, so it only produces beyond points C and D. Explain explain how decreasing the area, right, decrease the area over which the turbulent flow would increase the range. Now, just by them stating that decreasing the area for turbulent flow, that means there is more area for laminar flow, right? And laminar flow is very streamlined, right? There's no mixing, there's nothing. So what we can say from this is that there is less air resistance. There is less air resistance because there's less turbulent flow to go against, right? There is less air resistance. And because there's less air resistance, right, we can say that so more kinetic energy is used up for the flight. Or you can say that less EK is wasted going against air resistance. Now, what does that mean? So if I have a golf ball, right? So if I have a golf club, right? I have a golf club and I have this ball over here. If it had no dimples, it's going to travel only this much. If it had dimples, it's going to travel much further because, so this is dimples. This is no dimples. That's because if there's dimples, there's less turbulent flow, so the golf ball can travel much further, so that increases the range, right? So we can, at the end, it's always nice to say is wasted going against air resistance. Sorry. So this increases the range of the golf ball. So what are the 2 points we have said of the golf ball? We have said 2 points. We have said that there's less air resistance. I can go back to normal, sorry. There's less air resistance. And that's why, because, and then the second part is less kinetic energy is wasted going against air resistance. So that is our second point. Maybe increase it this much. Yeah, this is fine. All right. Next part. What is meant by Newton's first law of motion? Now, there's a lot of definitions for it. You can remember the text of definition, which is a body is at rest or moving at constant speed. In a straight line, it will remain at rest or keep moving in a straight line at constant speed unless it is acted upon a force. Or the easier way of expressing it, you can say, you can just write velocity is zero or constant if the sum of forces, which is, resultant force, is zero, right? You can say that, the resultant force is zero. And then you can say velocity is not zero when the resultant force is not zero. Now that makes more sense, because if we have a resultant force, there's going to be an acceleration, right? And if there's going to be an acceleration, there's going to be a change in velocity. Let me just make this one a bit clear. That looks like a plus sign. Velocity is not equal to zero when there is a resultant force, which is not equal to zero, right? So Newton's third law identifies pairs of forces. State 2 ways in which forces in a pair are identical. Now there are many ways the forces in a pair are identical, so I'm just going to list all of them. So if we push something, we're receiving a pull. If we push something, the other body is pulling us. So we can say that, identical, they're acting at the same time. We're not talking about part C, which is how they differ. So they're acting at the same time. That's one, right? They're the same types of forces. What else? They're acting at the same time. They're the same types of forces, and the same size, right? The same size, so the same magnitude, same size or magnitude. You can write magnitude if you're trying to be fancy. Magnitude. So state two ways in which forces in the pair differ. Now this is where I was saying something. I was saying if I'm pulling, let's say, a door handle, right? If I'm pulling the door handle, the door is exerting a push force onto me. So what's happening here is they act in opposite directions. Opposite directions. And they act in different bodies. Act on different bodies. Now this will come in handy when we do part III. So the question says, one of the forces acting on the car is being described below. The earth exerts, so let's look at the key terms here. The earth exerts a downward gravitational force of 2000 newtons on the car. Now we want to know it's Newton's third law pair force. So we know that the bodies are going to change, right? So we know, I'm going to just do it in a different color. So we're going to say the car exerts, right? Now it cannot exert a downward force, right? It must exert an upward force. Upward. Now the gravitational force stays the same. The gravity is the same force. Gravitational force, right, of 12,000 newtons, the same size, right, on, and that changes on the earth. So we only changed what? We only changed the direction and the bodies, right? That's all we changed. So I'm just going to maybe highlight this. So that's that, acting at the same time, same types of forces, same size magnitude, opposite directions, acting on different bodies. And over here, the car exerts an upward force, gravitational force of the same size on the earth. Okay, now, question number 15. You're asked to determine the acceleration of free fall at the surface of the earth using a free fall method in the laboratory. You describe the apparatus you would use, the measurements you would take, and explain how you would use them to determine G. So a classic. So what do we have in our laboratories? So we have, you can write apparatus or equipment. We usually have what? A ruler. You probably need a ruler, a timer, a data logger if you have one. What ideally you'd want one. And light gates, right? You'd want light gates and data loggers. So it's always good to visualize what's going to go on. So suppose I have this meter ruler, right? I have this meter ruler that I have. So if I have this meter ruler over here, and there are light gates, right, that are going to measure, that we're going to check the speeds against, right? So we have light gates. And we have, let's say, we take markers for every 10 or 20, 10, let's say 10, right? Let's say 10. Let's say we take 10 meter readings and we drop, let's say, an object, right? We drop an object, right? We drop the object. We're dropping at different heights, right? Dropping at different heights. So this is our experiment. So how are we going to do this? We're going to drop an object at different heights, and record their corresponding velocities, right? Corresponding velocities at the certain heights, right? So we're now recording the velocities, right? So we're measuring v, right? So we'll have a table. So draw a table of results for our velocities with our corresponding heights. So we can just write velocity and height, right? And we can't really use it to find our G, can we? Because we don't know what A is, right? We want to find out what A is. Now, height is just another distance. And we can use the following. We can use the following. We know that V squared equals U squared plus 2AS. And by definition, we know that u is 0, right? So we know that v squared is going to be 2gs. And now, why is it gs? Sorry, why is it 2gh and not 2as? That's because the acceleration we're trying to find is g, right? So that's why we replaced it with g. And our s, we have replaced it with our corresponding heights. And that's why we have h. So what we can do is we can find what g is, right? We can do v squared over h. And that gives us 2g. So if we draw a graph of, so we can write plot a graph of v squared versus height. So this is v squared and height. We'll get a linear line, which is the gradient of 2g. So we can write gradient equals 2g. So g would be gradient divided by 2. Gradient divided by 2. I know I've missed an a, but gradient it is. So give one precaution you would take to ensure the accuracy of measurements. So one easy one is you measure your distances at 90 degrees. Measure your distance markers at 90 degrees. So there is no parallax error. There is no parallax error. Okay. So question number 16. A horse is pulling a canal boat using a rope of 12 degrees to the direction of motion, right? Direction of motion. The tension in the rope is 1150, so 1150 newtons. The canal is moving at a steady speed. Calculate the resistive force opposing the boat's forward motion. Now, that's a mouthful, isn't it? So the motion is this, right? This is the motion. Tension always acts in the opposite direction of the motion. So tension must be in this direction. So tension must be in this direction, which is 1150. Now we want to find what? We want to find work done, right? How do we find what work done is? We have to find the horizontal component. So T cos 12 would be the horizontal component acting in this direction, right? So we can find that, right? So T cos 12 would be our answer. So T cos 12 degrees, so that would be 1150 times cos 12. That would give us 1124.8 newtons, which we have to round to. We can round to 1120. Why? Because the question shows us it's 1150. It's three significant figures. So our answers must be three significant figures. 1120 newtons. Next, calculate the work done on the boat when the canal boat is towed 500 meters along the canal, right? So we can say what? We can say work done is what? Work done is usually force times the distance, which from distance you can write d, or you can write s for distance as well. So the force we know is what? We can use the previous force on 1120 times 500. That gives us so 1120 times 500, that gives us 5600,000, and that is in I believe joules, because work done is also energy, right? 560,000. You could have also I'm pretty sure you could also write Newton meter. Newton meter is also a correct form. So if you were to write Newton meter, so if you were to write 5,600, so 560,000 newtons, Newton meter, this is also correct. So don't be don't be afraid if you write this you'd be wrong. No, this is the same thing, because initially I thought it was Newton meters, and I looked back, I was like, oh, it's also joules. So the next part, explain why using a longer rope would allow the horse to do the same work while producing a lower tension in the rope. Now let's go back to the rope itself. Now what are they saying? They're saying use a longer rope. Now if we use a longer rope, right? If we use a longer rope, we can go much further away, much further away, and you can see we can have a much smaller, so let's say this is, I don't know, 3 degrees, yeah. So we can have a much smaller direction. We can have an angle that is close to 0. Why is that important? Because t cos theta, right, is what we want. So t cos theta is the horizontal tension, right? That's the horizontal component that we need to find. The closer theta is to 0, right? Theta is to 0, the closer the tension is, right? The closer the tension is to the actual value. So if theta decreases, right, then cos theta is more closer to 1. So it's more closer to 1. More closer to 1. So we do not have to apply as much tension. So what we can say, or what we can write, right? We can write the longer rope means smaller angle. So cos theta is larger. So cos theta, you can write the cos theta is larger. So that way we can write cos theta is larger. And because the angle is close to 0, so we need a smaller force. Smaller force is required for the same amount of work done. Smaller force is required for the same amount of work. For the same amount of work to be done. Same amount of work done. So what have we said here? We have said cos theta is larger, right? Or it's closer to 1, and so hence we only need a smaller force. This is just the end part of the question where you write what the question asks you to talk about. But otherwise, the 2 points are cos theta is larger because the theta is lower. So I can also put that as our the key point here. So theta is lower because of the longer rope, which we have shown in the diagram, right? We can have shown it here, over here. So that's why. Question number 17. In the 15th century, an explanation of projectile motion went as follows. So we have that explanation, right? When you throw an object, it's called impetus. The main thing is they show us the diagram shows the path, right? This is obviously not the path of a normal projectile. This is not what we do anymore. It's different. So we have to correct the diagram to show the path followed by the projectile according to modern observation. So they're saying assuming it has the same initial direction. Now because we're saying that it has the same initial direction, we can correct the diagram and we can go further and we can make it a parabolic motion here. So that's parabolic motion here. All right. Explain why a projectile follows the path that the one I have drawn. So we can talk about initially, so we can write initially, so I can talk about from here to here, I can say maybe. So I can talk about so from like here to here, I can say the air resistance is pretty negligible. So I can say, so initially air resistance is negligible because you're not that high up. Negligible, you're not going as high up. Negligible, right? So the horizontal component is unaffected by gravity, right? So you can just go forward, and you can say that this part over here. So that's the first part. The second part I can say is over here. You can talk about this downwards part. I can say, what can I say? We can say the downward direction. So the downward, not downward, but downward direction is due to gravity, not the loss of energy. Downward direction is due to gravity or acceleration due to gravity. I'm just going to write acceleration due to gravity. That's a better physics term. Acceleration due to gravity. Acceleration due to gravity, since that gravity, because that's what this G is responsible for vertical component. And now we can talk about the horizontal component. So we can now talk about this distance here. So how much it travels. So we can say the horizontal component is unaffected the horizontal component is unaffected by gravity, because there are two separate components, is unaffected by gravity or acceleration due to gravity, or if to be on the safe side you can write IG. Okay, that's why. If you move down, when a toy balloon is hit quickly up an angle, it appears to follow the similar path, the one described by the 15th century explanation. So explain why the balloon follows this path. So the path they had, right? They had from here to here, and it goes straight down. That's the path they had. Now, how can we explain this for a balloon? So a balloon has a lot of air in it, right? So we can say the balloon, right, has a very high air resistance, right? So we can say, so we can just state, right? So a balloon has a very high air resistance, right? So let's say it's traveling by some velocity v, right? But when it reaches max height, right, what happens to it? What do we know about parabolas and general projectile? When it reaches max height, velocity is 0. And because velocity is 0 at this point, so we can write at max height, because the balloon reaches in max height, because the balloon reaches 0 velocity, the parabola ends. Why is that? Because now it's just going to fall vertically, because it has 0 velocity. So it will fall vertically because nothing is moving it anymore. It's not a projectile. It has a very, very high air resistance for vertically. Okay, so now we know. So we can say a balloon has a very high air resistance to the balloon, so it decelerates horizontally as well. So I didn't say that. You can also cite over here. Decelerates horizontally. So that's also another key point that you can add in to add to your 3 marks. So what are the key marks? The key marks are stating that the balloon has a very high resistance and that decelerates horizontally and vertically, and at max height the balloon reaches V0, so it will fall vertically down. So let me write vertically down. Okay. Question number 18. The diagram shows a submarine and one of the forces acting on it. The submarine moves at a constant depth, speed, and speed. So constant depth is important and constant speed is important, right? So what can we see here? We know a couple of forces acting on the body, obviously. We can say, what can we say? If there's an upthrust, there must be an equivalent drag, right? So you can write drag or air resistance. So I think you have to write drag, yeah. And then we can write what? We can write, let's say, we have drag because it's going away from the motion. We can write upthrust, right? Upthrust. And it has to be equal distance apart, which is weight. Because they tell us it's constant depth, so upthrust and weight are equal, right? And thrust and drag are equal. That brings us to the next question where it says state 2 equations to show the relationship between the forces. So we can write upthrust equals weight, right? And thrust equals drag. And why? How did I come to this conclusion? Why? Because they tell you that it's at constant speed and constant depth. Now, if let's say upthrust was bigger than W, then that would mean the submarine, so I'm just going to call the submarine, was going upwards, which is not the case, right? It's constant depth. And let's say if our thrust was bigger than our drag, that would mean that it is not going at constant speed, this is accelerating, which is not what they want, right? So they don't tell you this, and we're not going up, right? We're not going up, are we? It's a constant. So that's why we can say that upthrust is equal to weight and thrust is equal to drag. Okay. The submarine has a volume of 71,000 meter cube. Show that the weight of the submarine is that, and that's the density. Now, where do we go from this? You've been given all this information. Let's now work it out, right? So we know that give us density. So let's write density. So let's write the formula for density. Density equals mass over volume. We have two of these things, and we need to work out the weight. Now we know weight is what? Mg. All we need for weight is m, because we know what g is, and we can work out what m is using this equation. The density times, so 1030 times 71,000 is our mass. Now we can plug it in to our weight and we can write the exact same thing. So we can just write copy, and we can go paste here. This times 9.81 times 9.81. It's always good to at the end write or use a calculator for our answers, so that we don't lose marks for rounding incorrectly. 9.81. So we get an answer that is a long decimal, right? So I'm just going to round it 7.17 times 10 to the power 7. Now remember what I said? We said that I usually do more than one decimal place in my answer, and then I write what the answer should be. So the answer should be 7.1 times 10 to the power of 7 newtons. And why did I do 7.1 and not 7.17 or 7.2? Oh, actually, I should have done 7.2. What am I saying? Sorry. I meant to say, why did I do 7.2 and not 7.17? That's because the question is a show that question. So we can't just show it's 7. We have to show it that it's one more significant figure. So always remember, show that questions, one more SF answer. And then that you can remember as like a tip. And I can search one more answer for show that questions. All right, that is the answer. So we can now circle it. 7.2 times 10 to the power 7. All right, next question. Part D. The submarine can control its depth by changing its weight. This is done by adjusting the amount of water held in the tanks. As the submarine dives to greater depths, so it's going down, there's an increased pressure. So we can write pressure increases as you go down, which produces a compressive strain. Now compressive strain, you can think of it as squeezing Play-Doh. So we can say that when a material is undergoing compressive strain, the material itself decreases. The material decreases from its original length. Decreases from its original length. Think of it as squeezing Play-Doh, but the Play-Doh cannot change its material. It just keeps decreasing in its like thinness. That's what's happening. The original length was something. So if you imagine you have Play-Doh here, you have squished it. So now it's more like this, and just you keep on decreasing it from its original length. The thinness is decreasing, right? So the thin with this now it's much thinner, so it's decreasing from its original length, which is not good. So if you're in a submarine and this happens, more water can easily break through, and you can potentially lose the submarine to the water. So this decreases the volume of the submarine. Explain the actions to be taken to constant depth as the volume of the submarine is decreased. Now because the volume is decreasing, what's happening to the density? So if you think about it, mass over volume, if volume is decreasing, right, the density is increasing. And the only way we can get rid of it is if we get rid of water. They have water in the ballast tank, so what we have to do is we have to get rid of water. Get rid of water, so the weight decreases, right? So the weight decreases, or we get the same density as the sea, so it's easier for us to go down. So weight decreases. So yeah, get rid of the water, so the weight decreases. This is why. So we can compensate for the decrease upthrust, because we're going down slowly, right? Because there's an increase in pressure and upthrust. Okay, let me just this is important. This concept is important, that if this is happening, get rid of the water. So the 2 points are get rid of the water, so we can because get rid of the water, that's the first part. So this part, so this is the first part, get rid of the water. Second part, so the weight decreases, so we can compensate for the decrease in upthrust. That's the main things. Submarine is made from steel, suggest materials such as fiberglass, which is made from a smaller young modulus than steel, be unsuitable at greater depths. So what is young modulus? Young modulus is stress over strain, right? If we have a smaller value for this, right, that means that it has a smaller range for which it can handle compressive strain. So that means that at greater depths, right, so like when the submarine goes down, so at greater depths, right, we have to always link back to what the question is asking, right? We can't just go off topic. So at greater depths, the fiberglass would experience more compressive strain. So the key word here is not compressive strain. So it would experience more compressive strain. So then what? What did we say it does? It decreases. So what do we know? What does compressive strain do? Compressive strain does what? It decreases the volume of the submarine. So we can say if it experiences more compressive strain, the volume decreases even more. The volume is decreased even more. Decreased even further. Which obviously you don't want, because if the volume decreases too much, the people inside can suffocate and they can die. So greater depths, the fiberglass would experience more compressive strain. The volume is decreased even further. Okay, or a larger decrease in volume, you can say. Question number 19. So we have a jumping toy. They've carried out some experiments. The toy is pushed down, compressing the spring. So this goes down, compresses the spring, compresses the string, compresses the spring. And then after a short time, the suction cup leaves the base and causing the toy to jump. So this is a compression force. So it's to do with Hooke's law. Explain the shape of section AB. Now what is AB? This is a very easy example. This is a gradient. Remember, it's very proportional. So we can say this part of AB is following Hooke's law. Hooke's law. Okay, pretty good. Next, explain why CD is horizontal. Now, what did the question say? The question said that the question told us that the suction cup adheres to the base and holds the toy down. Now, that's the hold the toy down, isn't it? When it holds the toy down, that means it's fully compressed. So this is when it's fully compressed. Fully compressed. So we can do this, fully compressed, following Hooke's law. Next part, show that the stiffness of the spring is about 1000 Newton meters. Okay, how can we do that? Okay, so let's look at what's going on here. So let's just take any point where it's horizontal, right? Where we can find a point and we can relate it back. So suppose we take 20 newtons, right? So this is the easiest one. 20 is pretty easy to take. So I'm gonna go blue. It's gonna go here. That's around here, right? That's around 19. Okay. 20 newtons, and we can go across to 1 point. That's 1.56. So we can go across to 1.9. So 20 newtons refers to 1.9 centimeters. So we go back down. So stiffness is what? So we know that F equals kx, right? And K equals F over delta x, or the extension. Now force we said is what, 20 newtons, and the extension was 1.9 centimeters. So now we have to convert it to meters. It's a very important step. We have to convert it to meters. So convert, or else we're not going to get the right answer. So convert, so that's going to be what, 0.01 is 1 centimeter, so 0.019 is our meter. So this is what, 20 divided by 0.019. So if we put this in the calculator, we will get, so 20 divided by 0.019 gives us 1052. So you can just make it 1010. Let me check. 0.019 1052 Newton per meter. Newton per meter. Yeah. So 1050, we can go back to maybe, let's say, 1050 Newton per meter, which we can round to, which we can say this is enough. It rounds down to, one second finger rounds down to 1000 Newton per meter, the stiffness. As the suction cup is about to leave, the compression of the spring is 0.018. Calculate the energy stored in the spring at this stage. Now this is 1.8 centimeters, right? What do we know about energy? We know that energy is the same thing as a half times force times delta x, right? Fx or kx squared, same thing. So force times delta x. So we can find out, we already know what one of these things are. We know what delta x is, which is 1.8 centimeters, but in meters is obviously 0.018. So now we need to go back to our graph and locate 1.8 centimeters. You go back, then we can go down. So let me do it here. So this is 1.5678. And this refers to what? Perhaps if we go, so this refers to maybe this, I think, a bit further. And if we go down, this is 16, 17, 18, 19. Okay. This is just a bit. So if I make the bit smaller, so if I go a bit more increase, so if I go now, nope, from here, that's probably around here. We're looking at around 19.2 or 19, let's just say it's 9.2 centimeters, or newtons, sorry, newtons, 19.2, or it's between 19, it's between 19 and 19.5. So any range between that should be fine, right? Should be fine. So we can write 19.2 newtons. And that should give us, if we're correct, so 0.5 times 19.2 times 0.018 gives us 0.17. So this is 0.1728 joules, which we can round to 0.17 joules, and that's it, 0.17 joules. We didn't round to 3 sig fig because 0 is already there, 0 point, so it's fine, 0.17 is fine. Calculate the maximum possible height reached by the toy. That's pretty simple. We know that it's we already have the energy, so we can do the energy 0.178 equals mgh. So height will be 0.17 divided by 7.3 times 10 to the power minus 3 times 9.81. So when you rearrange, just rearranging, so 0.17 all over 7.3 times 10 to the power minus 3 times 9.81. This gives us 2.37 meters. 2.37 meters, and as you can see, there is only two significant figures, so I'm going to do 2.4 meters as my answer. Let me highlight the 2.4 meters. I did not highlight this, so 1050 Newton meters. Okay, See an assumption you have made in the calculation. The assumption we have made is all energy stays constant, right? We have said that all the energy, there's no energy lost, right? So we can say no energy lost, no energy lost, no energy lost. So you can say that, no energy lost, or we can say all gravitation potential energy is converted into kinetic energy, right? Once it's going up, or I should say the kinetic energy is transferred to, see, all kinetic EK is transferred to GPE, gravitational potential energy. You can say that. You can also say that the all stored energy from the spring is transferred to the toy. So that's also something you can say. So that's that. There's no energy lost. All EK. Okay, part D. The student uses a camera. That's the key thing here. Use the camera to video the movement, and then they use it to find maximum height. Use the advantages. Explain the advantage of using the video camera over making observation by the eye. Now, we know the camera, right? If we use the camera to record something, there is no reaction time, right? We just eliminate the concept of, so we eliminate reaction time, error, because when everyone has different eyes, right? So whenever we look at something, we might blink at the wrong time, we might not see it. So this eliminates the reaction time error that we can have as our experiments. The second thing we can have is what? Because we have eliminated the reaction time, this improves what? This improves the accuracy, right? This improves our accuracy or accuracy. We can also say it improves our precision, accuracy of our measurements. So I'm just going to write measurements. Right? The student repeats this procedure several times and records the following data. So we have five values, right? They're all pretty similar, right? So they tell you mean, maximum height 0.45. Now you can see that this, and this, they're very similar. And then you have this result over here, which we call the anomaly. Yes. This is the anomaly. So we can say, why is the student justified in using 0.45? Because 0.36 meter is an anomalous result. That is why. Okay, so we're done. Thank you for watching. I hope you can share this with many people as possible, so more people can benefit from this, and I'll see you in the next paper.